All right. Hello, everybody. Welcome to the first 1W-MINDS seminar of 2026. Um, Today, I am extremely happy to have Stephen Becker here from the University of Colorado Boulder. He's an expert in randomized methods for numerical linear algebra and is going to tell us about some applications of those guys for big data. So I'm looking forward to the talk, and I'll turn it over to you.
All right, thanks for having me. So I'm going to talk about randomized methods, and I mentioned other than SGD. SGD is stochastic gradient descent, very common for training neural nets. That comes up a lot. I'm not going to talk about that at all. So I'm going to talk about randomized methods other than SGD. This is joint work with a bunch of people, especially my former students, Farhad, David, and Osman. I'm also going to go over some background and just a whole bunch of things, which is not necessarily my group's work. But I'm going to try to keep this like informative. So I'm not trying to claim that I did all this myself or anything like that. So let's start. So I'm going to have two parts to the talk. First part is going to talk about what I mean by randomization. In this case, this can be a randomized sketch. I'll talk about what I mean by sketch. So we're going to talk about that and different types of sketches, starting at simple, getting to moderate, and then getting to kind of complicated sketches. Then we're going to talk about applications, what could we use them for, linear algebra, and things like that. Okay, let's get started. So the point of what we're going to talk about is trying to reduce dimensionality of data. So we have a data set X, we have P features, N observations, and the whole point of this sketching is to make this smaller. So we're going to take P dimensions and try to turn it into P small dimensions. We're going to keep the same number of data points N. There's other approaches where you subsample data points. We're not interested in that for today. We're going to take the number of features and try to make it smaller. So we're going to do that. Often the reduction is linear or sort of linear, meaning we can write it as a matrix multiply. So the output Y is a matrix phi times X. Phi is our sketching matrix. Okay, so why would you do this? Well, we just want smaller data because everything will be faster downstream. You could do that for denoising. You could do that to visualize things and so on. But what I'm especially interested in is doing this for memory reasons. We're going to talk about one-pass methods where the matrix X is so large, we can't do much with it. If we make it small, we can do a lot more with it because we can fit into memory. Okay, so method one, our warm-up is PCA. We take the matrix X, we do the SVD on X. We have the left singular vectors U1, and use that as our sketching matrix. So this is not quite linear. We'll call it non-oblivious. What I mean is it looks like a matrix multiply. So let's see, can you see my cursor here? Okay, so it looks like a matrix multiply, so it looks linear, but the matrix phi depends on X, so it's not really linear. So we say it's not oblivious. You can do this, it's very common for denoising, for visualization, and so on like that. So it's sort of our standard as a starting place. Okay, but it depends on the data, and it's kind of costly. Okay, what else could we do? If we want to make things faster, we want a smaller dimension. Let's just choose some of the dimensions to keep. So we're going to subsample dimensions. In this case, we're going to subsample rows. So we're going to take P and make it P small by subsampling. We can write that as a matrix multiply if we want. So we're going to do the subsampling. And the question is, how do you subsample? So you could subsample uniformly at random. That's the obvious choice. That's nice because it's what we call oblivious. It does not depend on the matrix X. It's not that great because it's not that accurate. You can easily think of a counterexample where you can't give a guarantee for the performance. What is better is to sample in a non-uniform way, in some way that depends on the matrix X. So it's, we call this non-oblivious. It depends on the data, but it will give us better performance. So a simple way to do that would be look at the norms of the rows. A row with large norm should have a higher chance of being sampled. A little better way to do that is what we call leverage scores. Leverage scores are kind of like row norm sampling, only you're going to make it sort of basis independent. To be more specific, you do like a QR decomposition, and then take the row norms of that Q matrix you have there. This will then be independent of sort of how you represent it. Okay. Our third sketch I want to talk about is maybe our gold standard classic sketch. This is, we'll call this a Johnson-Lindenstrauss sketch. So the result goes back to the 1980s, very well known by now. I take a matrix phi. It could be a Gaussian matrix, a sub-Gaussian matrix. It could be Gaussian that I orthonormalize. But just think of a Gaussian matrix scaled appropriately. If I have some data points, so these are the columns of my matrix, I have n different data points in p dimensions. I'm going to sketch them by multiplying by this random matrix phi, which is p small by p. P small is proportional to 1 over epsilon squared times log n. And if I choose that with the right constant, then we have the following result, which says that if I look at the original pairwise distances between all points xi and xj, and I look at their distances after I project them into the small space, this ratio that is about preserved, up to this epsilon factor. So think of it as I have some points. If I look at these pairwise distances after I embed it into a smaller dimension, all these pairwise distances are approximately preserved. So any kind of downstream computation that depends on pairwise distances would be approximately correct. So the math of this was not especially complicated, but the really critical thing that sort of inspired a lot is that this does not depend on the original dimension. So p small depends on epsilon. If I want to have a tighter bound, I need to have more rows, a larger embedding dimension. It depends on the number of points, only weakly, but it's completely independent of the original ambient dimension p. So that's kind of very exciting when you apply it to data science applications. So in general, if you're looking at a non-oblivious or a data-oblivious sketch, this is what we call the gold standard. You can't really do much better than this without doing some kind of non-oblivious sketch. But we're going to try to improve on this with the future sketches by making it faster. Right, so what's the downside of this approach? This matrix phi is a dense matrix, so multiplying it can be quite slow. So to multiply it would take this p times p small times n operations, which could be slow. There's a few other issues that can come up too. There's variations here, as I said, any kind of sub-Gaussian works. You can make sparse matrices with somewhat okay results. And instead of looking at like pairwise distances, you could look at distances instead of over n points or an entire subspace. So it's been generalized in many different ways. Okay, so now I want to talk about our first structured sketch. We're going to try to take something like that Johnson-Lindenstrauss sketch, which is accurate enough for what our purposes are, but make it faster. So this goes back about 20 years. It goes by different names. I'll call it the FJLT for fast Johnson-Lindenstrauss. The idea is the following. Let's do something like subsampling, so maybe uniform subsampling. But rather than just uniform subsampling of whatever you see, we're first going to apply these two operators. D is a diagonal matrix with plus and minus ones uniformly at random on the diagonal, so it's a Rademacher diagonal. So it's stochastic. F is deterministic. It's an orthogonal matrix, something like a Fourier transform matrix. So a DFT, if you want it to be revalued, it could be a DCT or a Hadamard matrix, but something like a nice kind of orthogonal or unitary matrix. When I say nice, I mean like the entries are about the same size and magnitude. So Fourier transform is perfect. Every entry has exactly the same size magnitude. Okay. Now applying this is a lot faster than a dense multiply, because when I apply this to a single vector, multiplying d times a vector is linear time because d is diagonal. Multiplying f times a vector is log linear time because I use the fast Fourier transform. And then subsampling is sublinear time. Okay, so it's fast to apply. And they proved, so Elon and Chazelle about 20 years ago proved that you get some nice results similar to the Johnson-Lindenstrauss kind of results. We'll talk about some ways to see that in a little bit. Okay. So maybe the simplest way, there's different ways to prove guarantees. The simplest way that I'm going to follow up on in a little bit is one way is to say, I have guarantees for leverage score sampling. I didn't talk about that in detail, but if you do leverage score sampling, I hinted that it was a better way to do the uniform subsampling. Well, after applying the F and D matrix, the leverage scores are approximately uniform. So by doing uniform sampling, I really am almost doing leverage score sampling. So then I can use guarantees for leverage score sampling, but I only have to do uniform sampling. Okay, I'm going to skip this, some intuition from Joel Trop. The next sketch I want to talk about is sort of the odd one out. because the other ones I was subsampling rows, meaning I could write it as a matrix multiply, a matrix phi times x. In this case, I could write it as a matrix times vectorized x, but if I just think of x itself, it may be simpler to describe what do I do. I'm just going to pick out some entries. So I'm not going to subsample rows or columns, I'm just going to pick some entries. I'm going to sparsify the matrix. So it's sort of a natural idea. This was some nice analysis a little over 20 years ago. It's been popular since then. And that leads us to our sixth sketch, which is our first contribution of our group in this area, where we're going to take that subsampling but add a twist. So we're going to combine the two previous ideas that we saw. So that FJLT, the idea was that I could do uniform row sampling after I have these F and D operators applied. Well, let's do the same idea. Let's apply those F and D operators to my matrix X. We'll call that temporary result a Y. And then I do this entry-wise subsampling of that. So that's our twist. So we're going to do entry-wise subsampling after, I'll call it preconditioning with this F and D matrix. Okay, so we do that. Why would we do that? Well, because when we do that entry-wise sampling, we're going to do that in a uniform way. Uniform is not a good way to do it if your entries themselves have irregular size magnitudes. If some of them are much larger than others, then you should do non-uniform sampling. But to do non-uniform sampling is a lot more complicated. You have to do another pass through the data and so on like that. So we're going to try to make sure that our data set is not too non-uniform by doing that preconditioning. So when we look at our analysis, depending on what you want to look at, most of the analysis depends on things like what's the largest entry you see. So we need some normalization. Let's assume that we're normalized by the column norm. So each column has norm 1. How large could the maximum entry of the matrix be? Well, it could be a 1. And that's going to be the worst case. That is, if we do uniform sampling, if some entries are very, very large, then we could have one entry as 1 and the rest are zeros. And we're very likely to miss it with uniform sampling. So that's sort of a very bad case. The best case, if we're normalized, is for everything to have the same size. So that would mean the maximum is the same as the average, which is 1 over square root of p. So what we can show is that after we do this preconditioning, afterwards, we basically have a very small chance that we're much larger than this best case scenario. So best case scenario is 1 over square root of p. Within a factor of square root log np, we're at the same level. Okay, so a little more concretely, we're going to look at estimating averages across different columns. I'll tell you why when we get to k-means. But so if I have all these different columns in my matrix X, suppose I want to average all those together, and figure out how large it is. Well, if I subsample, and so when I subsample, I'm going to call that x bar hat, and use that subsampled version to form my average. Well, then how far is it from the true average if I didn't subsample? Well, it's within t, and the probability of failure depends on t, and it depends on these other quantities, which depend on the maximum size of the entry and maximum row and so on like that. Well, and then how large is the maximum row and max entry? If X is this preconditioned matrix, then those things cannot be too large. Right, here's just plugging in some numbers. If I have a large data, even with large data, the square root of log term is small, it's 30. So the chance that I'm about 30 times larger than optimal is less than 1 over 1,000. So basically, by preconditioning, we're sort of putting us in the nice case where uniform sampling works well. Okay, let me skip this. Okay, our next sketch I want to talk about comes from theoretical computer science, and it's sort of slowly worked its way to numerical linear algebra. It's the count sketch. So here, phi is a sparse matrix with exactly one non-zero per column, and the non-zero entry is a plus or minus 1. The way to think about what this does is it takes a given row of the data matrix X, and you pick an output row uniformly at random, that is the location of this, and you flip the sign at random, and then you add it to there. And then if you have other rows that have the same output, they all get added together, okay, with their sign flips. It's very fast to apply because it's a sparse matrix. And so basically you loop over every entry in X. In particular, if X is sparse, you only loop over the non-zero entries. So when X is sparse, this is sort of as fast as possible to apply. Okay, so it's very fast to apply. Guarantees are not quite as good as our gold standard with a Gaussian, but they're good enough in some cases. And the proofs are a little bit different because they work on hash functions. You can think of a hash function as we're going to sort of pick the location to send these things at random. It could be completely independently at random, but for the proofs to work, they don't have to be completely independent. In fact, they only have to be two-wise independent. And we'll see why that's important in just a little bit when we extend this farther. Okay, so now we're getting to sort of the even more complicated sketches. We're going to talk about the tensorSketch, which is a special count sketch with a special choice for the hash function. But to talk about this, we have to talk about what kind of data are we looking at. So when I say structured sketches, in this case, we're going to structure our sketch to match the structure of the data. So if every column of our data matrix has a structure like this is a Kronecker product or a tensor product. If it has that kind of structure, so it's p-dimensional, and it has these v1 Kronecker v2, v1 is p1, v2 is size p2, then v is size p, which is the product of these. If I have that structure, I'm going to make a sketch to exploit this so that it's fast to apply. Okay, not really more accurate than a Gaussian, but much, much faster than a Gaussian. Okay, so let me go through some details. What is this Kronecker product? The Kronecker product, if you've seen it before, you know what it is. To remind you, or if you haven't seen it, we're going to sort of take this weighted sum of all the second terms here. So A has entries A1, A2, A3. I take this weighted sum, expanding that out, I get all of these things. Maybe a nicer way to think of it is if I did BA transpose, like an outer product, I get all possible combinations here. And if I vectorize that, so when I say vectorize, I mean take all the columns and stack them on top of each other. So vec is an operation that takes this matrix, gives me a vector. I can invert it with this matrixation operation. So if I do this and then vectorize that, I get exactly this vector here. So another way to think of it is that A Kronecker B is the vectorization of this outer product. You can do that with matrices with this very handy relationship here. I need to explain what a matrix Kronecker product is. That is the same thing, just sort of generalized. So A Kronecker with B means I take all the entries of A and take a weighted sum, weighted terms of these B weighted by those A matrices. So this gets large very fast. If A is I by J and B is K by L, so A has I columns, B has K columns, A has I rows, B has K rows. The output has the product of those, I times K rows. And same thing, the product of the columns. Okay, so it gets large fast. Another variant is the Cauchy-Rao product, which is like the Kronecker product, but only applied column by column. So for each column of A and each column of B, I do a Kronecker product. So I don't change the total number of columns. I need A and B to have the same number of columns, and I don't change that number, but the number of rows expands. The Cauchy-Rao product lets us introduce a notational shortcut. If I want to do the Hadamard product, that is pointwise multiplication of two vectors, one way to think of that is to take the transpose of A, transpose of B, and take the Cauchy-Rao product. That would give me all of these. These would now be one-dimensional. That would be pointwise multiplication, and then transpose back. So pointwise multiplication is just a bunch of transposes with this Cauchy-Rao product. This is getting us to the formula for tensorSketch. If you look at some works with tensorSketch and you see this formula is designed to impress. But we're going to try to unpack what is this formula doing. So the tensorSketch for matrix A, which has this Kronecker product structure, is given by this formula. I'm going to do a small count sketch on each of these small factor matrices. So I do this, then I do a fast Fourier transform. I transpose, I take the Cauchy-Rao product, transpose, take the inverse Fourier transform. So what's happening? If you're curious, I have more details in the appendix. I won't go through it in full detail now, but briefly, after I do these small count sketches, I'm doing a fast Fourier transform, and I'm doing this trick right here. I'm really doing some pointwise multiplication. I'm doing pointwise multiplication in the Fourier domain and then inverting the Fourier transform. So that's a circular convolution. And the way to think about it is, well, a circular convolution is really like polynomial multiplication with a certain modulo. So the way you think of count sketches is as polynomials. I do some polynomial multiplication, and that's what this convolution style operation is doing. Okay, so all this stuff is to say, I do some small count sketches and do a circular convolution. Okay, so it's quite quick to apply. That's the main benefit. I don't need to apply anything to the full-sized input matrix. I do everything to these small factor matrices. Okay, so we can go through the complexity quickly. If I just have an input is a single vector of size p1 times p2 with this Kronecker product structure, when I apply the tensor sketch using this trick we talked about, it's very fast because I do a small count sketch to each factor. So that's p1 plus p2, and then the circular convolution is this p small times log p small. So it's very fast. If I did a count sketch, but I didn't do this tensor sketch trick, it's slower, but still fast because count sketches are fast. And if I did like a Johnson-Lindenstrauss transformation with a Gaussian, it would be even slower. It would have this kind of complexity. So the tensor sketch is not quite as accurate as a Gaussian, but much, much faster. It doesn't need just two factors. It could have up to q factors for any q. The larger q is, the greater the savings. So here I have a sum of all these q factors, as opposed to the naive, I would have a product of all these q factors. Okay, so now our last sketch before we get to applications. This was proposed by this paper in 2018. And let me explain what we're doing. So we're going to do this sort of same trick we've seen before. We're going to do this fast Johnson-Lindenstrauss transform, where we do a diagonal matrix, a Fourier-like matrix, and then subsampling. Only we want to apply it to tensor structure data, or anything with this Kronecker product structure. So rather than writing f and d like this, let's split them up, and we'll say we'll have little f and little d, so f1 and d1, and f2 and d2, which are of the appropriate sizes, and we'll take their Kronecker product. So it's not equivalent necessarily to the original thing, but it's similar enough to give guarantees. And if we apply this to some vector, so if my vector has this Kronecker product structure, and I apply this, well, then I have this sort of distributive property where I can write it like this. And when I write it like this, I'm doing these little operations and the smaller dimensions, which are much faster. So I do those little operations, and then I would form the Kronecker product of those things and subsample. Only it's even better because the subsampling I can do implicitly. So I never form this final Kronecker product. Rather, I can subsample from it implicitly without having to form it. Okay, so this has been proposed for a while. It was analyzed in 2021, and we came up with a different analysis, which is better in some ways and worse in other ways. We can do it for up to q factors. And so if our data points have this structure, then as long as our output embedding dimension has size p small larger than this quantity here, so we have 1 over epsilon squared, as is common. We have a bunch of log factors. And as q grows, we have a 4 to the q. So if q is fixed, it's not a big deal. If q is growing, then it's not a good result. Then we have a result that looks very much like the Johnson-Lindenstrauss style result. We can approximately preserve pairwise distances. And the way we prove it is this trick I talked about, that when I do this half of the FJLT, the preconditioning half, it takes the sizes of the entries and makes them all about the same. So our leverage scores are now almost all the same size. Therefore, if I do uniform subsampling of that, it's about the same as leverage score subsampling. I can use those guarantees. And you just got to keep track of all the approximations. Okay. And just to compare, here's the gold standard result with the Gaussian. I still have a 1 over epsilon squared. I have log n. But the difference is that our operation is much faster to apply because it's structured. So if our data has that structure, we can apply it much faster. Okay, so that was all the sketches I want to talk about. Now I want to get to some applications here. Okay, we're going to start with linear algebra. Traditionally, linear algebra has been one of the big use cases for these sketches because it's well understood, but it also makes it hard as a use case because it is so well understood. That is, our baseline methods for linear algebra are already very good. So I'm going to talk a bit about linear algebra, but then move on beyond linear algebra. So for linear algebra, there's many different things you could do. Let's take a look by example for least squares. So least squares, I want to solve this problem. I have, say, an overdetermined matrix A. I want to find the minimum value of this residual. Okay, how could you do this? Well, okay, maybe in class you first learn about the normal equations. You can solve it with the normal equations. Not a great way to do it because it's not that stable. A better way is the QR decomposition. You do a QR decomposition. So if I have a QR decomposition, I've solved the problem. Let's forget about that for a second. Suppose I have a QR decomposition. Another way to look at it is if I have a QR decomposition, then this matrix A, if I multiply it on the right by R inverse, I get the matrix Q, which is orthogonal columns. If I did a Krylov subspace method, like LSQR, MinRes, things like that, then you can bound the conversion speed by the condition number. So if you precondition, this is in a different sense than I talked about previously. This is a more traditional preconditioning. If I precondition, in this case, the condition number is 1, and a Krylov subspace method would converge in one step, which makes sense because you can solve this in closed form if you have the QR decomposition. So what these two papers did about 2010, Blendenpick and LSRN, said, okay, doing the QR doesn't buy me anything, it's a standard method. What if I sketch the matrix, phi times A, and do a QR of this sketched matrix? Then that's faster because it's a smaller matrix, so the QR decomposition is faster. If I use that R and precondition A times R inverse, it's not perfectly conditioned. The condition number is not 1, but it's very good. It's like 2.5, which is very, very good. So if I do any kind of standard method like LSQR, it's going to converge very fast. Okay, so they show that if you're very careful, this can work a little faster than the state of the art on some kinds of matrices. It's a nice method because it fails gracefully. So for all these sketches, we have a theory that says you take this many rows, where you take like order 1 over epsilon squared. In practice, well, what does order 1 over epsilon squared mean? Like I need a number. How do you choose that number? Well, you pick a number and try. In this case, if you try a number and it's not the right number, it just means that your Krylov subspace method won't converge quite as fast as it should. It'll still work and it will still eventually converge. That's in contrast to other methods. Here's maybe the most straightforward way, the sketch to solve method, where I take my residual and I just sketch my residual. If I solve this method, if I don't choose enough output size for phi, if my p small is not large enough, this can fail catastrophically. So this doesn't give you high accuracy. So this is not great for like a drop-in replacement for a LAPACK routine, but it does have a place, especially in problems where think of B as like each entry in B is the output of a simulation. You can query B if you need to, but you're not just given B. So if I chose my sketch phi to be like a row sampling sketch, then the rows I don't see, I never need to even evaluate B at those rows. So for use cases like that, it's not even comparable. This just has lower sample complexity. And you're doing it for that reason, not for flop count for the actual linear algebra part. So, okay, that's my little introduction to linear algebra, like using sketching for linear algebra. You can use it for other things like SVDs and so on like that. But let's move on to some non-linear algebra applications. Okay, we're going to start with k-means clustering. And before I get to this, I want to talk about one of the big use cases for what we're going to do is to make one-pass methods. So let me describe what is a one-pass method. So we think of a data set. Say you have a giant video that's hundreds of terabytes. You could put it on a hard drive. But if you want to analyze it and do something with it, you're going to have to load it into your main memory, into the RAM of your computer, and do stuff with that. So it sits on your hard drive, but it's too big to put into your RAM all at once. So you could load it chunk by chunk. Every time you load it is very slow because you're pulling it from disk. That's a very slow operation. And often that's going to be much slower than the processing you do on it. So you're going to have to load the data set once from memory, but can you avoid having to reload it, right? So you load it once, but once you load a chunk, you have to throw that chunk away to make room for the next chunk. So if you want to go back and revisit that first chunk, you would have to reload it from disk. That would be slow. So every time you load the entire data set, it's one pass. Think of it kind of like an epoch if you're used to stochastic gradient descent. Okay, but we want to minimize the number of passes through the data. Okay, maybe a simple example is computing the sample variance for a data set. Okay, so if if I have the sample variance, I have some data points xi, they could be scalars in this case. What's the textbook formula for sample variance? Assuming you don't know the sample mean. Well, you compute the sample mean, which is just this average here. And then the sample variance, you look at how far does each data point deviate from the sample mean, square it, and then normalize it with this correction here. Okay, that's a valid way to do it. This implementation suggests a two-pass method, meaning we do one pass through the data. I do a for loop here. I load each data point xi from memory. I add it to my running average, and then I normalize. And then my second loop through the data, I again call this up from the hard drive, do some computation, and get my answer here. Okay, so there's nothing wrong with that, but it takes two passes through the data. So if each time I have to query this from a hard drive is slow, then this is fairly slow. But you can do a one-pass implementation of the same mathematical quantity. So motivated by this common expression for variance, we're going to use the fact that rather than writing it in this form, I can sort of do some some algebra tricks and write it like this. So here I would set two counters to be 0, load the data. Once I have xi in memory, I use it as much as I can. So I'm going to update this running average for mu hat, and I'm going to update this average for the square of it. So I'm going to use this xi as much as possible. Okay, so I'm not really saving flops because here I have two for loops and I do sort of one thing in each for loop. So it's like 2 times n flops. Here I have a loop of n and I do two things, so it's the same flops, but it's one pass through the data because while xi is in memory, I don't have to reload it for this computation. And then I do my algebra to get the answer here. Okay, that's just an example. It's not a good way to do the sample variance because it's not numerically stable, but it's an example of one pass versus two pass. Okay, so what's the connection? The idea is that with sketching, we could take a large data set where it's so large you couldn't put it in the memory of your computer, but by sketching it, we can make it small and to fit it into the memory of your computer. So you do one pass to create the sketch, and then afterwards it's in memory and you can do as much as you want with it. It doesn't count as a pass to the data because it's on the sketch data. Okay, that's the big idea. So let's apply that to k-means. K-means, let me go briefly over this. Many of you are familiar with this, but k-means is a method to cluster. So suppose I have, in this case, 8 data points in p dimensions. K-means defines a cluster by its mean. So it's going to pick a mean. So we're going to start by initializing, just pick whatever random means you want. So you choose, say, a number of clusters, let's say 3 clusters. You choose random choices for the means. That's what the stars represent. Then for each mean, we're going to perform an assignment step. So we say, okay, which data points belong to which mean? We just find the closest mean to do the assignment. So then we get this sort of Voronoi diagram. Once we have the assignments, we recompute the means by setting them to be the actual mean of the data points. So say the blue, I'm going to set that to be the sample mean of its actual data points. Okay, we do that. Then you just repeat the process. Again, you find assignments. Once we do assignments, make some new assignments, and then we recompute the averages, and we get something like that. And in this case, after those steps, we've actually converged. Okay, this is called k-means. More specifically, this is really Lloyd's algorithm. It's the way to solve k-means. It's not necessarily giving you the best solution, but it does converge, and it's a very common thing to do, right? So there's 100,000 papers written on k-means. Well, we're going to write one more paper on k-means. Let's try to speed it up, and in particular, try to make it in a one-pass method. So we assume we have a large data set. Okay, so looking at this, what do we do? Well, standard k-means takes our data set. We have n points in p dimensions. We're going to update the cluster centers and then update assignments. Let's take a look in particular at this assignment step. So for this assignment step, for each data point, I want to figure out which of the k clusters does it belong to. So I have this one data point xi. I have n of these data points. For this given data point xi, I compute the distance to each of the means, right? There's capital K of these different centers, and I compute the distance to each of these. This distance is in p-dimensional space, so that costs me order p flops. I do that for all capital K possible means, and then I do that for all possible data points. So I have capital K means, n data points, and p dimensions. So the cost of this step is k times n times p. And I needed the full data set. Okay, well, our idea is let's subsample. But we're not just going to subsample the entries. We're going to first do this special kind of preconditioning. I'm going to take my data matrix X. I load it into memory, maybe chunk by chunk if necessary. I apply D and F, the diagonal matrix and the fast Fourier transform. Those are fast to apply. And then I subsample it. And then I store this. This is now a sparse matrix, and I assume that I can store this subsample version, Y prime, in memory. Then I can throw away the original data. So it's a sort of a one-pass method. I load X. I do this operation here, chunk by chunk, subsample chunk by chunk, and then I get this sparse matrix. Now, for all these operations, everything's faster. I still have this K and N complexity, but this P is reduced because when I'm comparing things, I only look at the non-zeros. And so if I have like P small non-zeros per row on average, then this becomes like a P small. So it's a little faster, although it depends on the implementation, but the main benefit is that I can fit it into memory. So I don't have to reload it from hard drive every time. Now, this is why I had this theorem about sample means, because for K means, I want to find the sample means. We show that, okay, if we do this, then by subsampling, if I've preconditioned, which makes sure that these max row norm and max entry terms are not too bad, then I have a nice result saying that there's not much error when I do this. Okay, we apply this, of course, to MNIST, because everyone does that. MNIST has these digits 0 through 9. It's 784 dimensional. We have 21,000 examples. We're going to focus just on 3 classes. So it's really a classification problem. We're going to treat it as a clustering problem, just to simplify things a little bit. So we have, I'll look at 0s, 3s, and 9s. Here are just some examples. And we're going to compare, so we have the true cluster centers. Let's compare with k-means. Just baseline k-means, no subsampling. This is, in fact, not a large data set, so I can put this in memory. So I could do k-means, put it in memory. And if I do clustering on k-means, then I get some clusters. I look at the averages. They match very well with the true clusters. Okay. In fact, it's clustering, not classification, so I don't know the assignment. So for visualization purposes, I know this is actually a 0, this represents a 3, this represents a 9. So I'll put them in the same order. Okay, what else could we do? Well, we could just do subsampling, this entry-wise subsampling without that preconditioning, where I just pick some entries, subsample, and then find these sample means because of that. That will be faster, and it's one pass, so it's nice, but you can see visually it doesn't look that good. You know, there's definitely a loss in quality. As of the time of our paper, some other methods in the literature we tried, they also didn't work very well. Even some that were more than one pass didn't work that well. But if we do our method, where we first precondition and then subsample, still one pass, our results are basically identical to full k-means. Okay, so it works quite well. To be a bit more quantitative, on this left plot here, I'm going to look at the accuracy, my training accuracy on k-means. So if I have pure k-means, I have about 92% accuracy. And then I'm going to take my subsampling scheme. So red is just simple subsampling, no preconditioning. And I'm going to look at how much I subsample. So as I go to the right, I'm not subsampling very much, and it approaches k-means accuracy. As I go to the left, I subsample a lot. It's very fast, but accuracy goes down. If I do my preconditioning, my preconditioning is much more accurate than not doing preconditioning. And we have a variant. If you're allowed a second pass over the data, then we can improve things even more. So I have this 2-pass method where it's a little slower because it takes 2 passes, but the accuracy now matches k-means until about, say, 0.02 subsampling. So it's much, much faster. We did this on an actual large data set. So we picked this infinite MNIST data set where the number of examples is almost 10 million. This is now 56 gigabytes. That's larger than the RAM for some laptops. So we're going to assume our laptop only has, say, 1 gigabyte of RAM. We'll load it chunk by chunk. Well, the naive k-means has to reload that from disk to RAM every time it passes through, every iteration of k-means. If we do our method, where we do this one pass method, that's the sparsified version, we get a speed up of 40-fold because we're reducing the number of times we load it from disk. Okay, there's a small price to pay for accuracy, not too much. Okay, the next topic I want to talk about is tensor factorizations. So we're going to have to talk about tensors a little bit. For this section of the talk, I'm going to change notation a little bit. Script X is going to be a tensor, so an n-way array. The sizes are I1 by I2 up to In. We'll have matrices, vectors, and scalars. Tensors come up all over the place because most data is naturally a tensor. We have matrices all over the place because we take tensors and force them to be matrices because we know how to work with matrices. But a lot of data naturally is a tensor. So you have sparse tensors. Examples would be like the famous Enron dataset has all these links between users and keywords and days. So user 1 sent an email to user 2 about keyword X on day 3. We have things like that for, say, academic papers, who co-authored what with whom, and so on. We have dense tensors. A lot of these come from scientific simulation. So suppose we're doing a combustion simulation. Here we have a 3D spatial grid, and we have time. So already that's 4 dimensions. And then we have different variables, like maybe we're looking at oxygen concentration, CO2 concentration. So we have all these different variables, maybe velocities, and so that's another dimension. So in this case, we have 5 dimensions, 3 of space, 1 of time, and 1 of variables. So we have a 5-way tensor. Okay, so with these tensors, they come up all over the place, and you might want to do things with them, process them, compress them, and so on. That's what we're going to talk about. So, a lot of these things have a time index, and they come in one index at a time, one time index at a time. And so we're going to think of them as a streaming method, where we want to do our one-pass methods so we can store a smaller sketch of them and don't have to revisit them, or we can't revisit them if we can't go back in time. Okay, so to talk about tensors, we have to talk a little bit about some operations. First operation is matricization. So we're going to take a tensor and turn it into a matrix by reshaping it. So this n-way reshaping, or unfolding, the mode 1 unfolding takes a tensor and takes these mode 1 column fibers and stacks them all together. So for visualization, I'm always going to do a 3-way tensor, but of course you can do these for 4-way, 5-way, and 6-way tensors and so on. The big jump is from 2 to 3. We can do this with row fibers. So the mode 2 unfolding is going to take these rows, stack them together as columns, and stack them like that. And then a mode 3 unfolding is going to take these tube fibers and stack those together at the columns of this matrix. So these are just different ways to make a matrix out of a tensor. What else do we want to do with a tensor? We want to multiply it. So we're going to talk about multiplying a tensor times a matrix. So the dimensions have to match the right sense. And we define this, you have to say in what way do you want to multiply. If we multiply along the 3rd mode, what does that mean? Well, we can write down a formula to define it, which is not very illuminating. A better way to think of it is, if I say y is x mode 3 times a, then if I matricize it along this 3rd mode, then I can write it as a matrix multiply. So as a matrix times a matrix. So we take our tensor x, which is like this, the tensor, matricize it along the right mode, and we'll put it on the right, so now it looks like this. We multiply by a on the left, we get a new matrix, we invert that matricization back to a tensor, and we get our output right there. Okay. So once we have those in place, we can now talk about decompositions. To generalize the SVD, or an eigenvalue decomposition, there's different ways with tensors. One such way is the Tucker decomposition. The Tucker decomposition decomposes a tensor x as a core tensor g, which has the same number of modes as x. And then we have all these mode-wise products of these factor matrices. And these are now matrices. So g is a tensor, and these a's are matrices. Okay, so you could visualize it like this. The size of g has the same number of modes as x, but the dimensions of each mode could be much, much smaller. We call these the rank. So this tuple R1 through Rn is the rank of the tensor. And if these are small, then this picture is accurate, and this red core tensor really is much, much smaller. And you can just see by counting degrees of freedom, we've done some compression. We have many fewer data points to store. So why would you do this? As I said, you could do it for storage. You could do it for analysis. You do it for fast operations downline, and so on. Okay, so let's talk about this Tucker. How do you compute the Tucker decomposition? Well, the bad news is, unlike pure linear algebra with the two-way tensor, where you can do the SVD in closed form, in a sense, you cannot do the same thing with three-way and higher tensors. So you have to do an iterative method that may not converge to the right thing. So there's different iterative methods. In general, we want to solve this problem. We want to say, I have this data tensor X. Find the best core tensor G and factor matrices A1 through AN to minimize this. Ideally, this value would be 0. Solving that is a non-convex optimization problem, and we cannot guarantee that it's always going to work. But we can still attempt to do it, and it's still useful. There's different ways to do it. Maybe the simplest one is alternating least squares. Alternating least squares says, I observe that if I fix all but one of these, so if I fix G and A2 up to AN and leave A1 unfixed, solving for A1 is now a linear least squares problem, and I can solve that with standard linear algebra. Same thing if I fix A1 through AN but leave G unfixed, I can solve for G or any of these. So if I fix all but one, I can always solve for the other. Okay, that's the idea behind alternating least squares. So we're going to take that as our starting off point and try to improve it to deal with some things. Okay, so here's another way to rewrite that. I'm going to loop through all the factor matrices. And for the little nth factor matrix, I'm going to fix all the other ones, all the ones that are not equal to little n, fix those at their previous value. I'm going to do some linear algebra to reshape this. I'm going to matricize it. I fix the core tensor. And then this is my nth factor, and I'm solving for that one. I solve for that one, and this is a linear least squares problem. So I can solve this with standard linear algebra. And similarly, the core tensor I can solve like this. Now, I'm sweeping some details under the rug because in general, there's some tricks where if you orthogonalize things, then many things simplify and so on like that. But this is the general idea of what you want to do. Okay, well, what are some downsides to this? If you have a large tensor, it might not fit in memory. So every time, if it doesn't fit in memory, every time you solve this, you have to load it up from memory. So that motivates us to say, can we sketch it so that it now fits in memory? We don't have to load it from disk every single time. So that's sort of our main goal. The flop count is a little expensive, but it is a little complicated there because the standard method has these tricks that sort of reduce that. But in general, the sort of making this and loading it from disk is maybe our dominant cost. So we're going to try to deal with that. Well, we're going to deal with that by sketching. And here's where we're going to use the tensorSketch. So we're going to do a tensorSketch on this tensor here after we've reshaped it to a matrix and solve this problem. By doing so, this thing is now smaller. We can fit it into memory. We don't have to load it from disk again. But think back, so we talked about the tensorSketch and the details of it. It's a bunch of little count sketches put together. And that's important because what we're going to do is when we load the tensor at the very beginning, we're going to do a bunch of these little count sketches. And then each of these large tensor sketches is like a leave one out style. So they're going to reshare the same count sketches. That makes it a full one pass method. So we can load the tensor at once, do these little count sketches with a little bit of tricky programming, do those in one pass. And then from that point on, we have these sketches in memory and we can form these on demand, just doing some linear algebra. Okay, so that's the main benefit is we don't have to load it from memory every single time. We compared at the time to some other existing algorithms. We made a synthetic data set where we can increase dimension size. And as we increase dimension size, a lot of other methods run out of memory. Whereas ours, because we've sketched, doesn't have that same issue. We actually have two variants. I'm not going to talk too much about this other variant, but it's just sort of sketching in a different location. Our two variants don't run out of memory. One's a bit more accurate than the other. And um, there is one method that does not run out of memory. It's this green one. The green one is FSTD1. It runs fast, doesn't run out of memory, but it's just not accurate. So our sketching is sort of a nice trade-off between accuracy and speed. We actually have some of a real data set where my student went outside his house, set up a video camera, walked in front of it. And I mentioned earlier, other than compression or fast operations, one reason for a Tucker decomposition is to do data analysis. So here we have a 3D data set, which is a video, 2 space, 1 time. If we have a Tucker decomposition, we could take that time factor matrix and do some like simple k-means clustering on that. If we do k-means clustering on that, we could then maybe identify, okay, at which frames was he walking in front of the camera? And that's what this little classification is trying to show. So there's background frames and walking in front of the camera frames. Can we determine that? So it's kind of a toy method, but it was just an application for how we could show that we can actually do this Tucker decomposition on a really large tensor. So this matrix, this video was 38 gigabytes, which is bigger than my student's RAM. So we split it up, did the one pass method, did our Tucker tensorSketch, and we actually got something which seems reasonable. We can classify roughly when he walks in front of it. So here's a frame. It's class 1, meaning it's just background. And then this is class 3, meaning we think something's happening. And so you can see it sort of worked. It's not really the best way to detect something, but it's an application to show that, yeah, you can do something there. Okay, I'm going to stop there because I don't have time for the last topic. The last thing is about optimization, but if there's questions or anything, I can take questions about that. But yeah, that's it. Thanks.
All right. Thanks a lot for a great talk. I'll stop the recording here and let people ask questions afterwards. So, let me see. There we go.